So when we talk about multiplication of vectors, there are three kinds of multiplications. So the first of it is when a vector is multiplied by a scalar quantity. So let me illustrate this with an example. So let's say you have a vector A, which is equal to, let's say, 3i. And if you have a scalar of value, say 2, then if vector A is multiplied by 2, then you get a new vector A dash, which would equal 3 into 2 times I, which would equal 6i. So essentially you multiply the scalar quantity with the magnitude of the original vector to get a new vector 6i, which is 2 times the size of the original vector. And if the scalar quantity is positive, if it is positive, then the direction of the vector does not change. It remains same. But if the scalar quantity is negative, then the direction will change. So the same rule would apply to a multi-dimensional vector as well. So let's say you have vector B, which is equal to, let's say, 2i plus 3j. And if the scalar is, let's say, 2 in value, then your new vector B dash would equal to 2 times 2i plus 3j, which would equal 4i plus 6j. So this is your new vector. So the second kind of vector multiplication is when a vector is multiplied by a vector. And within this you have two kinds of multiplications. The first one is what we call a dot product. So let's say you have two vectors. One is vector A and you have another vector B. So let's label this vector B and this is vector A, and let's say the angle between the two is phi. Then the dot product of A and B would be written like this. A dot B is the dot product, and this equals the magnitude of A into magnitude of B into the cos of the angle between the two vectors. Now you would see we've taken phi as the angle between the two vectors, but we could have very well taken 360 minus phi as well as the angle between the two vectors. And in which case you could have written this equal to AB cos 360 minus phi, and you would have got the same answer because cos of phi is same as cos of 360 minus phi. Now what you need to remember is that this dot product is a scalar quantity. That is, it has no direction. So you would observe that if vector A and vector B are perpendicular to each other, then the dot product of A and B would equal 0 because cos of 90 would be 0. And if they are parallel to each other, then the dot product of A and B would be maximum and to be equal to the product of A and B. What also you can observe is, let's make a magnified drawing of these two vectors. So you have vector A here and you have vector B here. So let's say you take the projection of B on A, which would be this, and let's call this projection of B on A. And if this is the angle between vector B and vector A, you would see that cos of phi is equal to projection of B on A divided by magnitude of vector B, in which case projection of B on A equals B times cos phi. Now let's get back to dot product of A and B, and what you would see is that you can write this A dot B as equal to A times B cos phi. And here what you would see is that B cos phi is nothing but projection of B on A. So you can write A dot B is equal to A times projection of B on A. What you would also observe is that projection of B on A is nothing but the x component of vector B. So likewise, if you rearrange A dot B, if you rearrange A dot B as B times A cos phi, what you would find is this equals, that is A dot B equals B times projection of A on B. And I would really like you to work this out just the way we have done this part. Okay, so moving on, if vector A is written as AXI plus AYJ plus AZK, and vector B is written as BXI plus BYJ plus BZK, then A dot B would equal AX BX plus AY BY plus AZ BZ. And I would like you to work out this problem remembering that the dot product of perpendicular vectors like say I and J would be 0.